It's my great pleasure to introduce Evita Nestoridi from Princeton, who's going to tell us about limit profiles, mixing, and Markov chains. Evita, please.
Thank you so much, Thomas, for the introduction and for the invitation. Thank you all for coming. I cannot see you, but I hope you're listening and that you're out there. So as Thomas said, there's a link on the chat, and basically I'm sharing it, hoping that, if I go too fast, you can just, click on these arrows to go back and see what I wrote before. And if anything doesn't make any sense, please don't hesitate to interrupt me and ask questions. So today's talk is limit profiles for reversible Markov chains in connection with cutoff and mixing times always. And it's easier for me to talk to you about these subjects via card shuffling. In particular, I will focus on two models. For both of them, we will have a deck of N cards and distinct cards. And our first model is the famous random transpositions, which was studied by Diaconis and Sashahani. So what do we do during random transpositions? We pick two cards uniformly at random with replacement, and we swap them. And the question is always in card shuffling, how long does this take until we are well shuffled? And I will make everything mathematical soon enough. But for now, just bear with me. As you know, this is a question that makes sense, hopefully. So Diaconis and Sashahani answered this question in the 80s. And it takes 1/2 n log n steps to shuffle a deck of N cards during random transpositions. Now, we will all agree that this is not fast enough. If you plug in N, is 52, it takes forever. But this model has its merits in biology when someone wants to study DNA sequences. This is work by Duret and others. In the Markov chain world, this is a very crucial model because new techniques were introduced. It was one of the first times that representation theory was used to answer the mixing time question, and we will see that soon enough. And even for the limit profile, once I define what that is, there was a new technique introduced based on this model. So mathematically, it has been extremely important. The second model that I will be talking about today is the star transpositions. Now we swap a random card with the top card. So we pick a card uniformly at random. And swap it with the top card. And again, we ask, how long does it take until we're shuffled well? And Diaconis has proven that this takes N log N steps. But his work is heavily based on work by Flato, Odlisko, and Wales. So I do want to mention them here. Now, these models are very well linked because you can think of the random transposition model as, you have the complete graph. Each node starts with a different card. And what you do is say you pick an edge and you you pick an edge uniformly at random and you transpose the cards at the ends of this edge. That's called an interchange process. Now, the laziness will be different for people who know what I'm talking about, but roughly this is how one can think of random transpositions. You can think of it as an interchange process on the complete graph. The star transpositions would be the star graph. where again, we pick an edge uniformly at random and we transpose the cards at the ends of the edge. And so this 1/2, where is it, turns into a 1 just because in the star graph, every edge is at most distance 2 from any other edge. So you almost have the complete graph once you take 2 steps. So this is just a motivation on why these two models are actually very closely connected, as we will see later on. It's just that one needs to take twice as many steps to shuffle. And the point with star transpositions is that as far as limit profiles are concerned, there has been a new technique developed to study them. But of course, this technique can be used in other setups as well. Okay, but for now, these are the two models, and this is roughly the question that we will be discussing today. If there are any questions on the models or the question, please don't hesitate to unmute yourselves, because now I'm going to continue. And continuing means that I will do the formal setup. So first of all, we're going to be talking about Markov chains, and the configuration space is a symmetric group in this case. So each configuration of the n cards corresponds to an element of Sn. For example, when we buy the deck of 52 cards, it comes in a specific order. This will be the identity element. You know, if we transpose, say, the top 2 cards, this will be the 1-2 transposition, and so on. And now I'm working towards that question of things shuffled well. To do that, I need to talk to you about the transition matrix. So if X and Y are, say, 2 elements of the symmetric group, we build up this matrix P, whose XY entry is the probability of moving from X to Y after 1 step. Now, of course, this entry is going to be different for the random transpositions and different for star transpositions. So you pick your favorite model and you build up this matrix. Let's just note for a moment that this is an n factorial by n factorial matrix in this case, so it's huge. Soon we will be talking about diagonalizing this matrix, and this is why I really want to mention that it almost sounds like an impossible task. So the transition matrix, we will denote it by P or Q if we want to refer to both models. The point is that we will start raising this matrix to large powers, and this is why we will need the eigenvalues later on. So P to the T, when evaluated at XY, this will just give us the probability of moving from X to Y after T steps. And the point is that as we let T go to infinity, this entry will start looking more and more like 1 over n factorial. So the transition matrix to a very large power will look like a matrix that has 1 over n factorial at every single entry. So for every X and Y, this will hold. And just to start talking about measures, we will put the X down there. So this is just some extra notation just to indicate that this PXT is a measure. And so we will be talking of convergence of measures. So PX to the T, we will be converting to the uniform measure in this case. Now, I have chosen to talk to you about the symmetric group. I have chosen to talk to you about the specific 2 models. Of course, one can generalize this setup to general Markov chain on a different state, and we might not be getting the uniform measure at the end, but for today, all we care about is the uniform measure. And so now we wanted to study this convergence of measures. And we're going to do this with respect to the total variation distance. So let's define what the total variation distance. It's basically just the L1 norm. So the first notation is the distance between this pxt to the power of t from u, total variation distance, is equal to 1/2 of the L1 norm. So in particular, instead of u of y here, I can put 1/n factorial, but you can imagine how this would have been if the stationary distribution was not the uniform measure. Just some extra notation. I don't want to have to carry this notation everywhere. So I'm going to write this as dx at time t. And usually we want to take the worst possible starting configuration. So we're going to take the maximum over x of dxt. Now, when you are working on a Cayley graph, just like we are, it really doesn't matter where you're starting from. The graph is so symmetric in some sense that it doesn't matter, but in a more general setting, this would be important. So the mixing time, which is the main question, the main first question, at least for today, it says the following. If you give me an epsilon, then I should be able to tell you what t needs to be so that dt is less than epsilon. So, I'm doing everything in discrete time, so I'll be writing minimum. And this is the main question. So when I say how long will it be after the deck is shuffled well enough? Well, epsilon captures how well we want it to be shuffled. And t was this n log n that I said. Soon I'll be writing the theorems more carefully. Actually, let's do this now. So the first theorem. Let's say the one by Diaconis and Shashahani for random transpositions. So for random transpositions, if we take n log n steps plus a little bit more, then the total variation distance is less than, times 1/2. The total variation distance decays exponentially. And then they also have a lower bound. So let me not put it as b. Let me just say, if we take this, this is what we get. While if we take a few less steps than 1/2 n log n, so minus cn, then the total variation distance is bigger than 1 to the e minus v. This is rough now. I'm not necessarily writing it absolutely precisely, although soon we will see that we actually know the precise expression. And let me just quickly write how this would change for star transpositions. So Diaconis proved that for star transpositions, if we change t to n times log n plus minus cn, then the same statements hold. So with a plus, you get that the total variation distance decreases like this, and with a minus, it's very, very close to 1. Any questions so far concerning the setup and the first theorems concerning the mixing times? Okay, so because now I'm just for a moment cut off, and then immediately we'll jump into limit profiles. And soon I do need my notes for some references. Okay, so the Cardo phenomenon. Basically, the theorems that I just wrote to you can be can be summarized in a picture as follows. So if we were to plot the total variation distance with respect to time, we start with a very big total variation distance, so everything is equal to 1 for a very long time, and things drop suddenly. So for random transpositions, for example, this is 1/2 n log n, and the window, how back and how forward we have to go, is of order n in this picture. If we are to write a formal definition, we would say that a Markov chain xt exhibits cutoff. Imagine of star transpositions of random transpositions right now at Tn with window Wn if, first of all, Wn is little o of Tn. Okay, so Wn will be linear in these examples, it's just n. Tn is of order n log n. Then if we take the total variation distance at time Tn plus a little bit more, so c times the window, and then we take, first we take the limit in terms of n, so we send n to infinity, and then we send c to infinity, then we want this to be 0, so this captures this part of the picture, the decay. And finally, if we replace the plus with a minus, then we are very, very big, we are 1. So whenever these three conditions, so wait, this last part depicts this part over here. So whenever we have these three conditions satisfied, we say that the Markov chain exhibits cutoff, oh, I did not write that. I wrote the definition, I did not write cutoff, so let's highlight that, exhibits cutoff. Okay, so this is a standard definition. Now we have many examples of chains exhibiting cutoff. We try to understand them more and more. There are some criteria that are necessary. There are some other criteria that are sufficient, and so on. The Markov chain community has been concentrated in cutoff a lot. However, today I want to focus on it's not necessarily a new notion, but it's a notion that hasn't been studied as much, and people have started thinking about it more and more. And that is the limit profile. The limit profile just says, okay, if you can, drop this limit, the limit as c goes to infinity, and define this as a function. Now, before I'm interrupted, it's not clear to me that this is always well defined, meaning that if we have a Markov chain that exhibits cutoff, and we say plug in the total variation distance at the cutoff time plus c times the window, and you take the limit as it goes to infinity, it's not clear to me that this exists. In the examples that I have mentioned, star transpositions and random transpositions, it will exist and it will make sense. But it is a question, when is this function well defined? And then the properties, is it continuous, is it differentiable? All these things are interesting to me. So whenever you can define this thing, that's great. Otherwise, you can play with lim sups and limits and so on. And the question, of course, is, can we find a nice formula for this limit profile, this phi of c? And so this brings us to the first theorem in terms of limit profiles, which was a recent breakthrough. At least I consider it a breakthrough. I really like this theorem. So Luca Tessier expanded the techniques, the Fourier analysis techniques of Diaconis and Shahani, and he proved that for random transpositions, at time 1/2 n times log n plus c, So this is the time that he plugs in. The limit profile is given by the total variation distance of 2 Poissons. This was first noticed by Matthews, so it was conjectured for a long time, and Luca proved it in his master's thesis, I think a couple of years ago or so. And in terms of the star transpositions, this is something that I put out on the archive a few months ago. So for the star transpositions, all the changes is the cutoff time. Everything else is the same. And even though I do know that these problems, as I said, are extremely huge in biology and so on, for me, the main interest of this is looking at the techniques, because they can be applied in other setups as well. And so these models are just, you know, the motivation to come up with new techniques. To answer this limit profile question that, as I said, hasn't been studied a lot. So let's take a quick look at it notes. A few examples where we know the limit profiles and how did we come up to know them. So some references. So Markov chains, whose limit profile is known. Some examples, of course, there are more. So I'd say one of my favorite examples is the Bayer-Diaconis riffle shuffles. So this is the way that people should shuffle, I guess. It's riffle shuffles means that, you know, you have a deck of cards, you cut it in roughly equally sized piles, probably 2 of them, and then you riffle. And then you do it again and again. And so not only they proved cutoff at 3/2 log base 2n. Let me also put the window here. So plus c, that's the window. They proved the limit profile as well. So the limit profile is given by the normal distribution, basically. So something like this. I think there is a constant here. That's why I need my notes so that I don't miswrite their theorem. And they do get an error term. Well, okay, n is going to infinity, so we don't need this actually. Okay. Yeah, so there are 2 phi here. So let's put a tilde here, meaning that this phi tilde is just normal distribution. And I think this is why we like the letter phi here, because usually you see the normal distribution appearing. So that's why the limit profile letter is also phi. How did they do it? They really just did it with, you know, brute force. They wrote down the formula. In this case, with riffle shuffles, you can really write down the transition probabilities in terms of the increasing sequences that you see in a permutation. And they really just did lots of Stirling's formula, some very smart computations, and they got this just by, as I said, brute force. Another example that is very nice is the Lubetsky-Perez random walk on Ramanujan graph result. So they proved cutoff at Tn being equal to d. So you have a deregular Ramanujan graph. I'm not going to go into detail just because it is an example. And they managed to prove that the cutoff time is this. Let's also write the window. So it's a square root of log d minus 1n. They also prove, as I said, the limit profile, which is again given by the tails of a normal distributions. This is just some appropriate constant A. And here they managed to get the limit profile because of the backtracking. So they studied the non-backtracking random walk first. So you are not allowed to go back where you came from. At time t, you cannot go back one step. But then since you are backtracking at the end of the day, you are actually able to do some sort of central limit theorem and get the limit profile. One last example for today, as I said, there are many, is the one by Buffetov and Nedger on the asymmetric exclusion process, so ASEP, when you have many particles, so linear particles, so on a segment of size n, if you have alpha times n particles walking inside, the limit profile is given by the tails of a GUE. And again, I'm not going to go into details here. Again, I'm trying to make the point that whenever you have some sort of asymmetric exclusion process, so you're on the segment, you have a bias towards a specific end of the segment, you expect more particles to lie at the end of the segment, and this is really captured by the Tracy-Widom. So if you have no idea what I'm talking about right now, don't worry, we're going to get back to the star transpositions and random transpositions in a moment. I'm just trying to say that in most examples I have seen so far in the literature, other than Lucas's theorem, there's no technique. It's more like there's some behavior, like some sort of concentration argument that really gives the limit profile. And so I think that now the community is starting to focus on this limit profile question, and we try to develop techniques so that this becomes, an actual subject of its own. Any questions so far on the setup, the theorems, the examples?
So what is alpha in example B? Sorry.
In B, it's a constant that they define specifically. I was too lazy to write it down.
Mm-hmm.
But if you look at the paper, this is just a specific constant. Okay. In terms of the degree, but the degree is 6. It doesn't change with that.
And the results are for both positive and negative C? It doesn't play a role?
Yes, C is in R. Yes, C is in R. Good. But that's an excellent question. I should have said that both in the theorems and here as well, that C is positive and negative. Yeah.
So maybe another one. Just curious, is there any heuristics why you have Poisson in this transposition, and here you have normal?
Yes. So at least for the for here with the Poissons, one really looks at the number of fixed points as you do random transpositions. So you start at the identity, everything's fixed, and you start transposing and you see less fixed points. And it turns out that this follows, well, at this time, this turns out to be this type of Poisson. And this is the limiting Poisson. So we know that random permutation, if you look at the distribution of fixed points, it's a Poisson 1. So this is really the heuristic here, and similarly for star transpositions. Here, as I told you, at least in this case, this is for the Ramanujan graphs case, for example, it really is central limit theorem that kicks in to prove things in the part B. I'm still in the process of understanding Buffetov's and Nedger's work. So other than, that there is a nice concentration argument, I cannot say much more. And then for the Diaconis, Biodiaconis, I mean, as I said, they really look at the longest increasing subsequences. And I think that this is also where a normal 0-1 kicks in. But not much more motivation other than some incredible computations. Okay. Now, okay, let me also get there. to start discussing a little bit, and we'll see how far we will get to things, I go back a little bit to the L2 techniques, so the mixing time techniques, and I want to start with an L2 bound. So if we have a reversible Markov chain, whenever I say reversible, just imagine that the transition matrix is symmetric. I just don't want to have to define this as well. So let P be a transition matrix of a reversible Markov chain. And as I said, just imagine that P is symmetric, that this is all that this means. And let's focus on Sn again, so that we don't have to think of general spaces. So we can write down the following inequality for the eigenvalues. So all of them are between 1 and -1. So here I should have been putting an equal sign here too, but at least for our models, that's not the case. They're not equal, so let's just not worry about it. So these lambda i's, actually, let me change notation for a moment. Let's call this beta. That's important. Beta 0, beta 1, beta n factorial -1. So these beta i's are the eigenvalues of P. And the fact that they are in absolute value less or equal than 1 is some standard graph theory argument. So we take that for granted. It's standard theory. Now, if you are, whatever it means, if when you're aperiodic, you're always bigger than -1, and whenever you're connected, you're irreducible, then only the first eigenvalue is equal to 1. And we have these conditions satisfied with our model, so I will not talk about it much more. Let me also talk about the orthonormal eigenbasis. So remember, P is symmetric, so we have the spectral theorem. So with orthonormal eigenvectors, which we call eigenbases, F0, F1, Fn factorial -1, all these are basically vectors or functions from Sn to C or R, whatever, to R in particular. What is important is the following lemma. So the L2 bound. So the general rule says that 4 times the total variation distance when we start at X squared is less or equal than, so we exclude the very first eigenvalue and eigenvector, and we write Fi squared evaluated at the X entry, and then beta I to the 2t. So this is an L2 bound, meaning that the L2 norm is equal to this thing. And this is just Cauchy-Schwarz that I'm writing over here. Whenever we have transitivity, so a random walk on a group, just like star transpositions or random transpositions, so that's the transitive case, we can get rid of the eigenfunction in this L2 bound. And roughly, this is the inequality that Diaconis and Shahani wanted to use for random transpositions to prove the mixing result. So the question is, how do you find these eigenvalues, beta I? And that's where they use so I don't think, I'll just write a few basic things, but I will not go into depth as much as I wanted, because I do want to get into star transpositions. So the first model, random transpositions. Basically what happens is that, actually what I'm going to write is true for both models, not just for random transpositions. It's true for any symmetric random walk on a group. So your transition matrix is similar to this matrix. I'll explain in a moment what that is. It is a block diagonal matrix. So everything outside these blocks is 0. P hat rho I is what we call a Fourier transform. So let me just define things. So these rho i's are just homomorphisms. In this case, from Sn to GL MIC. Mi is just a dimension. Homomorphisms. And it's what people call the irreducible representations. I'm not going to define these things. I understand it's a probability seminar, but if you have heard of these things, that's what these things are. And for the symmetric group, we have a complete description of what these things are. The Fourier transform at rho I is just the average. So if we start, say, at the identity, and we take a step according to the transition matrix, we average the value of the representation. In particular, for random transpositions, here we only have transpositions and the identity surviving. Everything else has probability 0 happening. And so far, maybe I've said a few things about this, what these things are, but maybe you're like, okay, how does one compute these things? What's happening? So the important idea that Diaconis and Shashahani had was what is called the Shor's lemma, that will imply in this case that all these p hats are diagonal. So this is the identity matrix of dimension mi, the same as here. And here we have the eigenvalue. And by taking traces in this formula, they could find an expression of beta i's in terms of the reducible representations and the transpositions. So this is what they did. This is all Diaconis and Shashahani. And I will move on because I don't want to spend more time on representation theory unless you guys absolutely want to. So yeah. I do want to say now that Teissier, as I said, extended the representation theory technique to study the limit profile. And roughly, I'm not going to write his theorem. I'm going to write something that theorem or lemma. It's more of a lemma. I'm going to write another version of his lemma, which appears in my paper with Sam Olesker-Taylor. In terms of eigenvalues and eigenvectors, that's something that hopefully all of us can understand, which says that if we take a subset, say, of the eigenvalues, I'm excluding the 0, 1, then the total variation distance when we start, say, at x, minus the following sum, so we only take some of the indices, is bounded by some error term, again, given by the eigenvectors and the eigenvalues. So basically, when someone can study the eigenvalues and the eigenvectors, this just says pick the main terms. This will be this Poisson thing, the total variation distance of two Poissons. This is what is going to give us that for a smart choice of I, and everything else is an error. They're tiny, so they don't play a role. So Teissier's lemma is actually better than ours in the sense that whenever you can use representation theory, this expression is going to be much simpler than what I'm writing down now. But this is a form that hopefully all of us can understand. And the reason why this is difficult is because rarely do we know the eigenfunctions. Yeah, if we're lucky, we might know the eigenvalues, but the eigenfunctions are much harder to get. And so in our paper with Sam, we have some examples like EARN models, Gibbs sampling, and so on, where we could get our hands on, but we also have a gazillion examples where we really need better computational power to understand the eigenfunctions and do this. For the last part of the talk, instead of focusing on this, I want to talk to you about what happens in star transpositions, because the argument is actually nice and simple. And again, I can avoid talking about representation theory to explain to you what's going on. So in star transpositions, the idea, the new technique is something that recently I heard Peter Sarna call soft comparison. I like that soft comparison title. The lemma says the following. So if you have two transition matrices, P and Q, so P for random transpositions, Q for star transpositions, so two reversible transition matrices on the same configuration space, so on X or say on Sn here, so that we don't overcomplicate, such that they commute. Why is this important? Well, then they are simultaneously diagonalizable. That's what it tells us in terms of the spectrum, and we are going to use this. So just for notation, let phi1 be the limit profile of P at cutoff time T, and let phi2 be the limit profile of Q at cutoff time T star. Then we can compare the limit profiles as follows. So their difference, I don't want to put starting points here, so let's assume transitivity for the lemma. Of course, I can write a version without it. So the difference of the two limit profiles is less or equal than the difference of their eigenvalues at the time t, all of it squared. So where bi's are the eigenvalues of P and Qi are the eigenvalues of Q. And here I should have taken different times. So notice these are evaluated at the cutoff time of P. These are evaluated at the cutoff time of Q. Now, there's nothing hard about proving this lemma. It really is Cauchy-Schwarz again. I mean, for someone who's familiar with playing with the diagonalization and the transition matrices, really there's nothing hard. The main thing here is that we have the same eigenbasis for these two matrices. And so if we didn't have transitivity, so let me write this here just to be correct, to transitive. If I throw away transitivity, then we also see the eigenfunctions appearing here. Again, this f, I, x, all of it squared will appear there. So very similar to what we have seen so far. And I'm saying that this lemma is really what gave the star transposition limit profile as well, because star transpositions and random transpositions commute. In fact, it was pointed out that any random walk, symmetric random walk on the symmetric group commutes with random transpositions. So if we apply it, P is the random transposition transition matrix. Q is the star transposition. Then PQ is equal to QP check. One can check it by hand for these two things. But as I said, one can prove it for any random walk on Sn, symmetric random walk on Sn, that this is true. So this is a nice property when you have a conjugacy class invariant random walk. It commutes with basically everything you would care about. And so what to prove the theorem, so that they have the same limit profile, which is what I wrote back then, one needs to understand that was a beta, not a Q. Let me look, beta and Q's is what I wrote. This is what one needs to understand, the limit as n goes to infinity. And so then one has to read the works of Flato-Odlyzko-Wales, where they diagonalize fully star transpositions. And even though these Fourier transforms that we talked about are no longer a constant times the identity, they turn out to still be diagonal. And roughly the important terms are roughly a constant times the identity. So what I'm trying to say right now is that the behavior of the eigenvalues is very similar. It's just that the time changes. And whenever you see that, you can just do this soft comparison. It's a technique that can be applied in other settings as well. Okay, so as I said, I will avoid going into specifics, even though I have written down formulas for you. I don't think it makes sense. This is a probability seminar. Instead, I will finish with a few open questions. I'm not sure they're necessarily easy. So the first thing would be to determine the limit profile for random to random. That's another card shuffle, where you pick a card uniformly at random, you remove it from the deck, and then you insert it into a randomly chosen position. Now, the importance of random to random for me, again, was that it brought a new method for diagonalizing transition matrices, a technique that I expect to see in different setups. And so I do believe that setting the limit profile will also be important because it will give a new technique. This soft comparison argument can be applied, but it will not give anything useful because the eigenvalues of random to random behave completely differently than random transpositions, for example. I do want to see hopefully more work in exclusion process. I think this is probably the most doable question I have to offer. So first, on the complete graph, if you don't know what the exclusion process is, you have a graph, you have k particles, and again, particles jump on neighboring sides from where they are. So the complete graph should be the easiest case. Still, I have looked into it and it doesn't look completely easy, but I don't think it is insanely hard. I believe that someone will be able to do it. Much harder will be the segment, where Laquan has proved, Hubert Laquan proved cutoff, but we don't even know the window in this case. And do I want to mention another model? Most likely these are the two open questions I wanted to offer. And most likely I'll stop here. Thank you very much for your attention.
Many, many thanks for the great talk. How about some questions for Evita? So for the first question, is it going to be Poisson as for the other card shuffles?
I would be surprised.
Oh, okay.
Yeah, the behavior is very different.
So
meaning
do
that
you have any reasonable guess? Is it Gaussian then?
No. So if we go back to this Fourier transform matrices, I remember the block diagonal matrices I told you about. Let's call it p hat 1, p hat 2, and so on. No, I mean, I don't have any reasonable guesses. This is the answer. And I'm just trying to say that for random transpositions, these are diagonal. Here, they're highly non-diagonal. And the point is that, for example, the first important block is roughly n-1 by n-1, and root 10 of the eigenvalues, the top eigenvalues, the biggest eigenvalues, are roughly equal, and the other ones are negligible. So this root n gave a very degenerate answer. So I didn't write that this is 3/4 n log n in terms of the mixing time, but we also have some extra window term, a very weird, which is due to Megan, by the way. So this is my theorem with Megan Bernstein. Megan really insisted that we get this extra log-log term. Back then, I wasn't so sure it was important, but now that I study limit profiles, I understand why this is important. This is greatly insane to me. Why does this thing appear? The only motivation I can give you is the lower bound was done by Ellior and Subag, who studied the cards yet to be removed from the deck at time t, and he proved that they need at least this many steps to see a random behavior there. So perhaps in his work, I think he might be doing it with some sort of CLT type of thing. In his work, there might be the answer that you're looking for. I don't remember what he gets exactly. His work is highly, I want to say technical. There are a lot of wonderful computations in there, but I think he will be giving the answer to your question. It's worth looking at it.
Thank you. Are there any other questions?
Could you please go back to page 4 of your definition of this cutoff?
Yes, did I write it correctly?
Yeah, I'm wondering what is the role of the C there?
The C?
Yes.
I mean, you know, how many steps of the window you take, I guess. And so
because why is it important in the definition of the limit profile? So what is the role of the C playing there in that cutoff?
Right. So let me go instead to these examples. It's easier for me to tell you in this theorem by Diaconis and Shahani. For random transpositions I wrote to you, if you take 1/2 n log n plus 1/2 times c times n steps, then the error is given by e to the minus c.
Okay.
So c appears in the error term, as you can see. You see? Over here. Yeah. So if you give me an epsilon, I can tell you take c to be log of 1 over epsilon to get the total variation distance less than epsilon, which is what the mixing time was.
I see.
Yes, yes. And okay. So, yeah, and then going back to the limit profile, I try to highlight that it's not clear at all why this is, you know, well defined, and you know, one can take the limit profile at time tn plus 2 times cwn, and this will be a little bit shifted and so on. But so this is not, it's a little bit, you know, playable in some sense.
So in your definition there, limit profile, your window wn is fixed.
It depends on n usually.
Ah.
So when I take n to infinity, this changes, but c does not change.
I see. Okay.
Only in the example of Bayer-Diaconis, it turned out that wn was constant. Okay, that's a very special case where this wn does not change, but usually changes with n.
Okay, thank you.
Thank you.
Maybe also one quick question. So at first you had this heuristic that, you know, the reason we have the additional factor 1/2 from one model compared to the other is that the diameter of the graph is 1 and the other it's actually 2. Is there some kind of, you know, geometric result? Do shuffling according to a graph? You know something about the distributions of pairwise distances? Can you get some upper or lower bound, something like this?
This is a great question, and I want to say there should be results like this, but I'm not sure I have read them. I mean, there are rough results using the diameter, but nothing sharp. So I haven't seen some geometric argument turning this 1/2 to precisely 1.
Okay.
I have seen geometric arguments turning this 1/2 into some other constant that is not sharp, giving n log n. But that's not what you want.
Yes, I see. Okay.
Yeah, the geometric arguments I have seen so far do not give cutoff.